Today we will be demonstrating how to determine the viscosity of an unknown liquid with respect to water at room temperature using Oswald viscometer. Basically, viscosity is the resistance which is offered by a liquid while flowing to other part of the liquid. This method that we are going to use to determine the viscosity of an unknown liquid is based on Poiseuille's law. The experiment that we are performing today, which is to determine the viscosity and then the concentration of the given unknown liquid, is based on a law which is known as Poiseuille's law, which is given by this equation: eta is equal to pi r to the power 4 into T into P divided by 8VL, where r is the radius of the capillary through which the liquid is flowing, T is the time of flow which is taken by the liquid to flow from one edged mark to the other edged mark, P is given as P is the value of hydrostatic pressure, eta is the value of viscosity coefficient and which has a unit of poise, V is the volume of the liquid in ml, and L is the length of capillary which is there in Oswald viscometer. All these parameters give the value of viscosity coefficient in poise, and 1 centipoise is equal to 0.001 Pascal second. Since we are using an Oswald viscometer and the liquids, one is the reference liquid and the other liquid under observation, are flowing through the same capillary, therefore the values of R, which is the radius of the capillary, the value of L, which is the length of the capillary, and the value of pi and the volume are constant. Therefore, eta is directly proportional to value of P, which is the pressure, and the value of time of flow. So the value of P can be substituted in terms of D, G and H, where H is the height of the column, D is the density of the liquid, and G is the acceleration due to gravity. So eta becomes directly proportional to D, G, H and T. Since the value of G is also constant if we are comparing two liquids, so eta 1 is directly proportional to D1, G, H and T1. Suppose there is another liquid which has a density D2, a time of flow T2, so eta 2 becomes directly proportional to D2, G, H and T2. So now if we divide these two values and take the ratio of eta 1 and eta 2, it becomes directly proportional to D1, T1 and divided by D2, T2. So using this experiment, we will be determining the densities and also the times of flow in order to calculate the ratio of eta 1 and eta 2, and then we will be considering 1 as a reference so that we can get the value of eta for the liquid under observation. Basically, we will be using water as a reference whose viscosity at different temperatures is already known. In order to proceed with the experiment, I will be showing you what all things we will be using. So the two main things that we will be using is this U-shaped Oswald viscometer, which has two glass bulbs and a thin capillary, and there are two edged marks here. And the other thing that we will be using is a specific gravity bottle which has a volume of 10 milliliters, and we will be filling it with first of all with the reference liquid, which is water here, and then with the other solutions that we have. So the solutions that we will be using today are 5, 10, 15 and 20% solutions of glycerol water, and there is an unknown solution which we will be using and we will be determining its concentration.
So for our viscosity calculation, we will be requiring density of each of our solution. So for calculating the density, we have the specific gravity bottle which you can see here. Now this specific gravity bottle has a volume of 10 ml. So what we will do that we will first measure the weight of this empty specific gravity bottle, which we can see here. Now what we need to do is we have to fill this specific gravity bottle with water. And we will then close the lid of this specific gravity bottle. So, water which is in excess from 10 ml will be out from the bottle, and we will have to wipe this bottle. So, we are just wiping this, the excess water which we had. So, this needs to be done properly so that we do not get the weight of any excess water present. We will now take the weight of this specific gravity bottle filled with 10 ml water. So that now we have the weight of both our empty specific gravity bottle and the specific gravity bottle filled with water. So what we need to do is that we have to subtract the weight of empty specific gravity bottle from that filled with water. From that we will get the weight of 10 ml of our water present in the specific gravity bottle. So we will fill the specific gravity bottle with 10 ml of our samples of different concentration of glycerol present, and we will then weigh them and subtract the mass of empty specific gravity bottle from each of the mass. From that we can get the mass of all different samples of different concentration of glycerol which we made. So these are the different solutions of glycerol which we made. We had 5%, 10%, 15% and 20% volume by volume solutions of glycerols, and then unknown solution of glycerol whose concentration we will be determining. So after weighing the mass of different samples or different volume by volume solutions of glucose and water, this is the observations which we obtained. So first of all, to measure the viscosity, we need to know the viscosity of the reference at the particular temperature. So we need to know the laboratory temperature in which the experiment is being done. So the laboratory temperature for this condition was 35 degrees centigrade. So the laboratory temperature in which this experiment was done was 35 degrees centigrade. Now the mass of empty RD bottle or specific gravity bottle obtained was 18.92 grams, and the mass of RD bottle, RD here is relative density, which we also call as specific gravity bottle, has a mass of 28.76 gram. Now these are the masses of different volume by volume solutions of glycerol which were added to a 10 ml RD bottle. Now what we did was we subtracted the mass of RD bottle containing water with that of empty RD bottle, and we obtained the mass of 10 ml water as 9.84 gram. Similarly, we obtained the masses for different glycerol solutions as indicated here. Now we already told that the ratio of viscosity of two different liquids can be written as eta 1 by eta 2 is equal to d1 t1 by d2 t2, where eta 1 is the viscosity of our reference liquid, which is water here, and eta 2 is the viscosity of our sample which we want to obtain. Now d1 here is the density of water, and d2 here is the density of the unknown sample or the sample whose viscosity we want to determine. Now t1, t2 are their respective flow times. So from this equation we can obtain eta 2 as d2 t2 upon d1 t1 into eta 1. Now this d2 t2 is the ratio of densities of unknown liquid or the liquid under study with that of water. We call this ratio as relative density. So density is mass per unit volume, so it can be written as m2 v2 and d1 can be written as m1 by v1. Now since our specific gravity bottle has a volume of 10 ml, so v1 here is equal to v2 is equal to 10 ml. So we can see that our relative density is m2 by m1. So since we had the masses for different glycerol solutions and the mass of water, we will divide each of the masses of different glycerol solution with water to obtain the value of relative density for different solutions. So we have the relative densities for different solutions. We will now use these relative densities to calculate the viscosity of these different solutions. So now we have clamped our viscometer into a stand. So we can see that this viscometer consists of two bulbs, and a capillary. Also we can see that this upper bulb has a 2 marks on its 2 sides. So for calculating the viscosity of our sample, we need to fill the viscometer through this portion, and we will then suck the liquid through this suction pump, and we need to raise the liquid above this mark. We will then allow the liquid to flow through this bulb, and we will start our stopwatch when the liquid reaches this point, and we will stop our stopwatch when the liquid reaches this point. So we will take the reading for each of our sample, the time taken between these two edges, and we will do this 3 times for each of our sample, and we will then average the readings, and then we will use these readings for our further calculations. So we will now start with first filling this viscometer with water. Now since we have this bulb filled, what we will now do is we will now suck the liquid to the other bulb through this suction pump. So we can see that when we suck it through this, the liquid level in this bulb is rising. Now that we have risen our liquid level above this mark, we will now allow it to fall through this bulb, and we will start our stopwatch when the liquid level reaches this point, and we will stop our stopwatch when the liquid reaches this point. We now have a stopwatch with us. We will now allow the liquid to fall through this bulb. So now that we can see that our liquid has flown between these two edges, so we will now do it again for the same sample, and we will repeat this thing 2 times more. We will then take the average of all these 3 readings and use these readings for our further calculations. So like we did for water, we will now repeat the experiment with our 5% glycerol water solution. Now we will similarly fill the viscometer with this 5% glycerol solution, and we will now note the time taken by this glycerol solution to flow between these two edges, and then we will do this experiment again 3 times and take the average of these readings. So now that we have taken the readings for our different concentration of glycerol, we will now proceed with the unknown glycerol solution. So in the similar way, we will fill our viscometer with this unknown glycerol solution. We will now suck it through this bulb. And now that we are above this mark, we will now allow it to pass through the capillary between these two edges, and we will note the time as the similar way we did for other samples. Now I will remove this section and allow it to fall through the two marks. So we can see that the liquid now has flown between these two marks, and we have noted the time for this flow. We will now repeat this experiment 2 more times, and in the similar way take the reading and average them.
Now that we have found out the time of flow for different solutions which were volume by volume solutions of glycerol water, we can use these values to determine the viscosities of these solutions, which can be plotted versus the concentration of these solutions, and the concentration for the unknown solution can then be determined.
So to calculate the viscosity of the different solution, apart from relative density, we also need their flow times. So this is the flow time obtained for water, and we took 3 readings for them, which were obtained as 70.8, 71.1 and 69.8, and then we took the average of these readings, which was 70.75. We did this for all other liquids, that is 5% glycerol, 10% glycerol, 15% glycerol and 20% glycerol. We also did this for the unknown liquid or unknown solution of glycerol, and we obtained the readings as 80.1, 80.3 and 80.1. So we took their average and it was obtained as 80.17. So all the readings are here are in seconds. So now we will use these flow times to calculate the viscosity of our unknown sample or the viscosity of different glycerol solutions. So now we previously told that eta 2 or eta of the solution under study is the relative density, that is d2 by d1 into the ratio of their time of flow, that is t2 by t1, into the viscosity of the reference eta 1, that is here water. So relative density we obtained from this, and flow times for different solutions we have in this column. So we can substitute all the values for 5% glycerol, 10% glycerol, 15% glycerol and 20% glycerol. So we obtain their viscosities as indicated here. Also we did the same thing for unknown glycerol solution, because we have the flow time for the unknown glycerol solution, and we also have its relative density with respect to water as 1.020. So we substituted all these values in this equation and obtained the viscosity of unknown glycerol solution as 0.83 centipoise. Now what we want to do next is to determine the concentration of this unknown solution. So what we need to do to determine the concentration of this unknown solution is to draw a plot between viscosity of the solution versus the concentration of solution. So for different solutions, which we can see here that 5% glycerol solution is here, whose viscosity is marked here. The viscosity of 10% glycerol solution is marked here. The viscosity of 15% glycerol solution is marked here, and the viscosity of 20% glycerol solution is marked here. Now these points are fitted in a linear equation of type y is equal to mx plus c. So here m is the slope of this curve and c is the y-intercept. So we obtain this equation y is equal to mx plus c. So here y, which is the viscosity of unknown liquid, which we obtained as 0.83, which we will substitute here. So we need to determine the value of x. So x here is the concentration of the unknown solution or concentration of any solution. So y is the viscosity of our unknown, which is obtained as 0.83. So we will substitute all these values in this equation. Since we have our y, we have our y-intercept as c, and we have the slope of this curve. So after substituting all these values, we obtained x as 6.9%. So which is the concentration of our unknown glycerol solution. So we we can see that the concentration of unknown solution of glycerol is found to be 6.91%.